by a population of neurons. I first give you some examples to see why is that the information has to be coded by many neurons, and then we'll get into the mathematics and how you can use that to describe the coding and decoding, that we can read out information from activity of a population of neurons. So this first example is called the motor cortical tuning. So this case, the monkey is reaching in some three-dimensional space. The simplest version of the experiment is like a two-dimensional movement. So basically the monkey's hand here is in the middle, and it can go center out in 8 different directions. So these rasters are spikes in repeated trials, moving in one direction. And if you plot the total firing rate, you get something look like that, right? The activity, the firing rate of a neuron is a function of an animal's direction of hand movement. Roughly like a cosine, called a cosine tuning curve. Of course, different cells have different preferred direction. All right. So the question is this. So we know the motor cortical cell controls movement. So if it's not just a couple cells looks like, the vast majority, pretty much all the cells look something like that, very broadly tuned. You don't see cells very sharply tuned. That means if the animal moves the hand in some direction, it must be driven by many different neurons. But for each individual neuron, you see their tuning is very broad. Right? It does not say the cell fires only when animal moving in a specific direction. It fires animal moving many directions that surround the preferred direction. The cell fire rate is pretty high. So you have a very precise movement of the hand. It must be, controlled by many of these neurons put together. Just individual is not that precise. So this is true for many areas in the motor system, related to motor system. The motor cortex, there's the cerebellum. As you know, it's very important for movement, learning, and also basal ganglia. That's also associated with motor movement and other learning. Even for some of the sensory cortex, it also have this kind of very broad tuning. So the broad tuning is very, very typical. All right. So the broad tuning means just based on the firing rate of a single cell, it's hard for you to tell what exactly the direction of movement, right? Because there's noise and also the tuning is very broad. All right, this is one example. I'll give you a few more examples like this, right? Of course, you know that has to be true. So this is the auditory tuning. You already learned some auditory tuning already, right? So this is threshold. I think this is the threshold of some auditory nerves as a function of a frequency. So suddenly, with this low threshold of this cell, that means that the cell really likes this frequency. It fires more to this frequency. Let's not say the cell only fires this, but they fire a range of frequencies. Some of the tuning curve is wider, but it's not just, there's just some width there, right? If you play some frequency somewhere, you activate a bunch of fiber in the neighborhood, right? So not just one, you activate many of them. So there's another example, different sensory modalities, somatic sensory system. This is a long hand, like an alien, that's like a monkey. Monkey hand looks like that, very long. And each of this oval, this thing here is a tactile receptor field. But if you touch the skin, the single cell in the motor, somatosensory cortex respond to the touch, but only for that particular area, if you are fully inside that area. So you go to the tips of the hand, there's receptor field is smaller, maybe smaller than some in the palm, but it's not that smaller. But it's, if you have a needle or 2 different needles, can you tell it's 1 or 2? You can actually tell pretty well, but that discrimination of the resolution actually is smaller than the size of the receptor field here. This is the somatosensory receptor field. This is the location on the body where the cell fires. So this is the visual receptor field. You have learned that already, I suppose. So this is from, I think, the ground squirrel in California. So each of the oval is the receptor field of a single cell in the visual cortex. So if you shine a light inside the receptor field, the cell will be activated. If you shine a light somewhere else, anywhere else, the cell doesn't care. So the cell only cares that small part in the whole visual field. When you go to the fovea, you see the size of the receptor field a lot smaller. But based on this, if you see anything at all, you can see lines much finer than this. Right? So you present anything in the visual field, it must be represented by population, with a population in the neurons, it's just many neurons, they have to act together, so their whole pattern of activity has to mean something outside. Right? This is different from a computer screen where your camera you have a pixel that only for that pixel. Anything else, you're supposed to be independent. Different pixels work independent of each other. So this is not, right? It's like locally there's some size. So given any stimulus, even a single point, you're going to activate many different cells in the neighborhood. All right. There's one more example that shows this problem even more clearly. This is the hyperacuity in the visual system. Right? So people are very good at this task. There's two lines, are they aligned or not? Right? Then you can move remember the offset extremely small, and see how small can you tell them, see the two lines actually have some offset. So if you project the image to the retina, actually the smallest offset when projecting the retina actually is smaller than the size of your optic sensors, right? It's maybe a third, but it's a fraction of the size of your optical sensor. About a half arc minutes. Basically, 1 degree can divide into 60 times. Just like an hour have 60 minutes. This is one degree. It's about you can separate in 60 minutes. So this is about a half arc minute. That's how the size of your sensor. So this one could have been used. It's called a vernier hyperacuity. So that means if you can tell the things apart so tiny, smaller than the sensor, you had to use information from many of the sensors, and not just one. And of course, you can use this kind of caliber. I don't think people use this as much today. People now use like a digital system, right? But this you can take advantage of that. You can really, measure things much smaller. Right? Otherwise, your eyes can't see. All right. So that's the phenomena. Okay. Here's the first method that had been used to read out the information from a population of neuron. So if you have say your camera have a bunch of pixels, I want to say where's the location of that dot. And you just say, find which pixel is most active. That's it, right? It's very simple. But if you have a neuron that's so broadly tuned, like the cosine tuning curve we talk about, so broadly tuned, if many of the active, where is actually that stimulus, right? That's a question. Where the movement direction? It depends. Some variable could be sensory, could be motor. Some variable is correlated with neural activity. So the first method, I think it's called the population vector. It's extremely simple. And I just explain this because this is the first example. Actually, I invented at Johns Hopkins. Today, people still use this kind of method. So for that, we go back to the reaching example. Imagine a bunch of cells in the motor cortex. They like some particular preferred direction, right? The preferred direction, the supposed D is the actual reaching direction. It has some angle in the polar coordinate system, all right? That's your actual hand reaching direction. So the firing rate of neuron activity A above some baseline, because that cosine function is always positive. It is sometimes a negative. You have to add some constant to make sure that even the lowest firing rate is not zero, all right? There's some baseline. All right, it's not important here. We always subtract the baseline. Just say that the activity above baseline A is equal to the dot product between the preferred direction P, I is the ith neuron, we have a bunch of neurons, the dot product with your actual movement direction, the reaching direction D, all right? So we know based on mathematics that's equivalent to the length of the vector, or the normal vector of your preferred direction vector, the D, and there's two scalar, and the cosine of the angle between the two vectors, right? That's a definition of dot product. So basically, the preferred direction, that's a constant. The direction of movement, you can change in different direction. So if the amplitude doesn't change, so difference is only the only variable is the angle, right? So this is the simplest model for the coding. Basically, you have reaching some direction. The firing is a cosine of the angle between if your actual movement direction is aligned with your preferred direction, so the angle, the difference is zero. That's one. If you move away from that direction, it's slightly smaller. If you are orthogonal, it's 0. If you go in other direction, it's become negative. All right. So that's just the description of that cosine tuning, like a very broad tuning. You can describe it as a dot product. Okay, here's the population vector. It's defined very simply. Suppose you have a bunch of neurons, right? I know the activity, AI, relative to the baseline. You suppose you measure their preferred direction. It's a vector which they like some particular direction, and you just like linear combination of all the preferred directions. Basically, all the preferred directions and weighted by the activity. That's a population vector. So basically, this is like a voting, right? Each neuron has has their opinion that you should move in that direction. Some other neurons say you should move in this direction. Other neuron goes the other direction, so on. Move in different directions. So some neurons are more active than others, right? So you weight their vote based on the activity. Some neurons who cry very loud, you vote more, right? Some neurons are, quiet, you weight less, right? And you add them together, it's still a vector. So that vector, in many cases, it can recover the true reaching direction. Right? There's an example where, in this case, all right, how all the black lines here, the segment, that's the vector of the movement for a particular cell. All right. For example, for this vector, this line, it's the same cell as in this case. Same cell as this case. So each of the panel is all the neurons record simultaneously. It's recorded in the repeated trial according to the active reaching direction in this direction. So the red arrow is actually reaching. This black arrow is the actual reaching direction, right? It's reaching 8 different directions. So the red thing is that population vector. So it's computed by averaging all the preferred direction vector like this. This particular neuron like this. No matter which direction the animal moves, it always prefers that direction, right? That's the same in all the panels, except for its length is weighted by the activity. So here the smaller, right? In this case, I guess it's probably, I don't know which cell, probably this one. Well, so on, but it's all weighted. But if the activity above it is negative, you weight in the opposite direction, like here, weighted. It's the same cell, all right? So basically each cell vote, you add them all together, it's a vector summation, right? What an active average. You see here, it's pretty much, you can recover the preferred direction, right? So in the past, people think, oh, maybe each neuron, the vote is more like generate some little force. You add the force together, that's total force moving that way. The idea is not exactly right, but this analogy is here. All right. Okay. So and also you can see this is not exactly right. Sometimes it's a big error, sometimes a small error, sometimes almost dead on, right? It's pretty accurate, but so there's some error. You ask the question, why you have to recover direction this way? What's the best method to read out the information, right? You want to read out information from the brain, right? To figure out what's really going on. So this is we ask the question, what's the best method? So first of all, why the population vector method actually works, right? And why can you improve upon this method, all right? This shows the population vector working in 3 dimensions. So this is the animal moving in the 3D space. So this plot, all those things are the preferred direction of all different kind of cells in the motor cortex. You see the cells, they like all kinds of directions. Right? They're pointing in all different directions. Some cells like this direction, some cells like others. So this case is that animal moving in 3D space, and if you do the population vector with all the vectors that are weighted, based on activity, then you add them together. So I don't know which is which, but this you can recover the actual movement direction in 3D space as well. All right. That's simple enough. So why does the population vector works? So this is the simple explanation. The actual idea is actually very simple. It's all because you have that cosine tuning, right? So we want to show is that the activity, right, the preferred direction vector P, weighted by the activity, sum over, that's the population vector. We can show that it equals to the actual reaching direction D if the preferred direction of these cells, you put them together, it satisfies this condition. This is the necessary sufficient condition. Right? It's roughly true if all the cells preferred direction are distributed randomly in a uniform manner. Right? So what's because it's condition? The condition is that this preferred direction vector as opposed to column vector. All right. The transpose is a row vector. So this product is an outer product, right? So it is a matrix. It's a matrix, right? You add this matrix together, you call the identity matrix. So that's a condition, the mathematics to make these things work perfectly. So if these vector P are distributed uniformly among all directions, this is actually true. This is actually true. Right. To see why this case is very easy. So because by definition, the probability vector is a weighted average of the preferred direction based on activity. You can write this way because this A is a scalar. You can move in the front or back, it doesn't matter, right? But you move here just for this convenience, right? Because this vector activity based on we said it is a cosine tuning is equal to the dot product, right, between the preferred direction and the actual reaching direction, the P and the D, right? So you write this way, this is the transpose is row vector times a column vector. So just as a MATLAB here, we assume every vector is a column vector by default, all right? So this is that dot product, right? Then you can write this way and put this thing first, like get the D outside of the parentheses. You see this is this whole thing, a matrix times D, all right? So of course your preferred direction based on point vector always a linear, it depends on, you know, this point vector and it relates to the reaching direction by this linear transformation. But this linear thing, if it equals to identity matrix, they're exactly the same. All right, that's a simple argument, very simple. All right. So in the motor cortex, people found this condition is roughly true. This condition is roughly true. So that's why this thing actually works in practice. All right. So why is that you want to use this method? Because you already know what's the actual reaching direction, right? Why do you want to just recover based on neural? But there is some other things that can be interesting. This is one example. It's called the mental rotation. Is that there's no behavior, there's no overt behavior. You cannot observe anything. That in the mind, if something is moving in the brain, you can use the method to read out that information. All right, even though there's no movement at all. So this is a sort of one mental rotation phenomenon. Is that if you give it a tool, just kind of blocks, right? It's like Lego kind of blocks. If you ask the question, are these two blocks identical or not? You can judge. When people do the task, the one phenomena is that the times for you to judge they're the same or different depend on the angle of different. I mean, you can rotate this, you know, Lego pieces to this one, you know, see how they are the same or not. And people usually do that in their mind, right? So if they're if they're the pose very similar to each other, you can rotate a little bit. That's very easy. If it's very different, you have to take a time to rotate. So the reaction time, the time it takes to do the judgment, is like a linear function of the angle between the two objects. Right? So that's evidence that you have like mental rotation. So this experiment is a simplified version for monkey. It's extremely simple. So it's like this. So the monkey's hand starts with here, right, in a two-dimensional environment. And the monkeys are supposed to reach toward not a visual target. Typically, there's a visual target. You see the monkey's hand in the middle of a circle. All right, there's on the periphery there's a LED light. Once the light is on, you can reach toward that light. That's like direct reaching. So this mental rotation task is kind of a simplified version. Is that when that light is on, say light down here. The monkey's hand here, you don't reach toward that target. Instead, you reach 90 degrees to the left. So you have to rotate the 90 degrees to the left. All right, that's monkey can actually learn this. Right, not direct. You turn to the left, no matter where's the visual target. So here, you can measure the different cells in the motor. This is in the motor cortex. Right, you see that. Before you have a movement, the activity already builds up. So it's over 90, has a 90 second. That's you show the target. So all these things, the different slices over time, the 200 milliseconds, a fraction of a second. That's before there's any movement. You can actually measure the EMG, you see there's no muscle movement whatsoever. It's all mental, right? So it's happening in the brain. So before your hand moves, in the motor cortex, some activity it's already start to build up. Right? So this is shown. So that activity, you know the preferred direction based on your measurement. That's a population vector. That means the cells basically start to vote toward that direction, which is sort of consistent with the visual stimulus direction in the beginning. They start to build up, and then look at the vector start to turn. Eventually, the neuron, like the actual reaching direction, start to be activated. And then, after a while, the hand actually start to move in that direction. You see this kind of activity rotation. So this is, just a tool you can interpret the result from many neurons. So each neuron by itself is very broad cosine tuning, right? It's hard to see the single cell, but if you put them together, you can read out this kind of information, right? That's one example, it's a very early example. So you can also use to do this hand position reconstruction to sort of like drive a artificial device. So this video is I'm not sure. So this is a recording from a neuron while a monkey's hand is moving. You can hear this Poisson kind of spike. You learn this Poisson kind of like statistical spikes, very random. All right. Wow. We know the brain is noisy. This is just too noisy. So it's triggered by spikes in the motor cortex. Yeah, that's very noisy. So based on the activity, you can hear the sound because this animal actually moving in a circular direction, a circular manner, right? This is can we see it? Yeah. So in this case, one ball. Let me see. So the animal is moving in the virtual reality. There's a visual target moving. The hand try to follow the actual visual target in that case, right? You hear the sound of that activity. So what we see here is that this direction, so the reconstructed hand position of this ball is calculated based on the population vector, right? So that means the population vector gives you an instantaneous movement direction. All right, that's a vector where you move. Okay, the next time step, you use the activity change, you use the new activity to compute the next time step of the population vector, that you move in a new direction, right? You just add the vector from head and tail and connect them together. They're basically like an integrated velocity. So population vector is more like instantaneous velocity for the hand to move. You integrate those things, add together, you can contract the whole trajectory. So that's what you saw. This animal actually moving in a circular direction. But they can do tricks. It's a virtual reality visual target. You can make the visual thing appear to be elliptic, right? Where you can really change the gain, right? To play different tricks to see whether the motor cortex follows the vision or follow the hand movement. All right. So this is robotic construction. So also based on population vector, if I can see this here, yeah. So this is two different panels. So the right hand side is a hand of a monkey pushing different buttons, right? On the left hand side is a robotic arm is driven by the population vector from many cell recorded simultaneously from motor cortex. So you based on activity, you construct instantaneous velocity or the direction of movement. Then you update that from time to time. So the robotic arm will move. But this example is an early example. Then it's not very convincing whether the robotic arm moving is exactly the same as a hand. So in your later example, I think it's better. In this case, as a monkey, the robotic arm is actually controlled by the population vector from the motor cortex. So this actually can be useful now, right? It is actually can be useful. Well, it's yeah, some part is harder, So you see, this is really this uses it's not a real arm. The arm is not moving. It's just based on thinking, right? Well, yeah, it's not kind of hard, but it's doable. Actually, can be. This already start to be useful, right? You can imagine this. And the little grip is actually added because the quantum vector is where you should move your hand, right? You can move, but once you reach some direction, that's thing, the grip, that's extra stuff. It's not controlled by the population vector. All right. So that's a population vector already used, but that's not the best method, right? There is a better method. So similar to this, we said the optimal linear estimator we considered before, right? With the optimal linear mapping, it's very similar to that. So the idea is that suppose you have a bunch of neurons, okay, their activity. I just explained this method, right? This is a better method. Some improvement. So this is the activity is a kind of cosine tuning. It's basically preferred direction dot product with actual directional movement d. All right. Suppose you have a bunch of neurons, you can write this in a vector matrix form, right? So now you see this is a matrix because each preferred direction vector here is a row vector because I transpose it, right? This bunch of a row, this is a matrix, right? You write this way. So you want to say that given this activity, you want you have a preferred direction times okay, see. All right. So you want based on So based on this cosine tuning, this equation should hold, right? Your activity vector should be related to your direction vector by this equation. What do you want to do? You see, you observe activity from the cortex, right? You want to read out the intended direction d, right? But how can you do this, right? We know this is like a pseudo-inverse solution, right? It's similar to the optimal linear mapping we talked about before. So this is a linear equation. You want to solve for d from A. So the P, of course, is not even it may not even be it's not a square matrix because you have many more neurons than the dimension. Dimension is either 2 or 3 dimensions, right? And do this is a pseudo-inverse trick, right? Just solve by pseudo-inverse, all right? Okay. This is the best method, right? Or which is like a benchmark method, I would say. So, so this method is based on a probabilistic theory. Is that what you have based on from your measurement of neural activity and some physical variable, right? Because X, it could be any variable, could be sensory or motor. Here the reaching direction, right? So what you have is this probability distribution of your responses, right? Given each the physical variable, the encoded variable X, right? So given this X, you have a distribution of that responses of the neuron, all right? So that's you can measure from the data. But once you have that, so this maximum likelihood method, I'm sure you use it in the statistics, right? It's just you find the parameter, which is the encoded variable, to make your responses. If your response is noisy, it's a probabilistic. You make your responses the most likely. Right? So basically, the maximum likelihood is kind of a little bit of twist, right? The idea is that you make your data the most likely, right? That also makes sense. And whatever data you have, you already got it. That's probably the most likely to occur, right? That's one way to talk about this. So this is that you maximize your data, the probability of your data, make that likely, right? So give a concrete example. Suppose you have a tuning curve, could be that cosine tuning curve. The tuning curve is what? It's basically the mean firing rate, right? This example. This firing rate as a function of the direction of movement, right? Direction of movement is your encoded variable X, all right? You have a mean firing rate, which here is a cosine function, that's a mean. But you also have an error bar, right? There is some probability distribution. So the simple thing is, okay, if the Poisson in the spikes that have a Poisson distribution, number spike per unit time window, that's the firing rate. If number spikes may have a Poisson distribution, right? Have a mean. The mean is that fx. That's called the tuning curve. That's basically the mean firing rate as a function of some variable. All right, that's a tuning equal. Like, of course, depend on the stimulus on the variable that's encoded, the x. So the actual response R, it has a mean equal to this fx, right? But the actual R every try will be different. Even you move in the same direction every time, the number spike will vary in time because the big noise we got already heard very clearly, very noisy. So you have this kind of distribution. So for Poisson distribution, the variance of the error bar with standard deviation is equal to the mean. Right? That's the variance equal to the mean. That's the, that's a Poisson. That's one feature of Poisson statistics. Or you can have a Gaussian noise model. Is that given x, the mean is equal to fx, right? That's the mean firing rate. So actual firing rate have an error bar, which is size is equal to some kind of standard deviation with a variance sigma square. So in this case, it will be the fx will be this cosine tuning curve. All right. The sigma will be the size of the error bar, which is the same everywhere for the Gaussian model. For the Poisson model, is that you have a bigger response, right? Bigger means the variance also varies, also bigger. Right? So that's actually closer to the truth. All right. So this is just two examples. So the maximum likelihood is just say that, okay, you give me some responses, right? you give me some activity. I'm gonna go backwards, see what's the variable, because the noise I don't know exactly, right? But I just make this probability the probability distribution just the same. It's two examples will be these two. Makes us most likely, makes us the highest probability. So why this method is the best method? Well, there is a mathematical proof. So this kind of method, if you have a big data, a sample many times, or many cells simultaneously with the same cell repeated in many repeated trials, as the data become large, all right? So this error you always have some error, right? Because because there's a noise. Based on the activity, you cannot for sure know what exactly is the encoded variable. There's always some noise, but that noise turns out have a have a lower bound called the Cramer-Rao bound. So you can read out information in many different ways. For example, the population vector or that optimal linear estimator. There are different methods to give you a different estimation. But their error, your method can be very bad. I'm saying always 1,000. That's you can always equal to 1,000. That's wrong. My method. That error can be extremely large. So there's no limit how bad you can be, but there's a limit on how good you can be. You cannot be better than a certain thing, right? That's the Cramer-Rao bound that shows that you cannot be better than that because you have an inherent noise, right? There is a minimum error you can achieve. So this mathematical method, if you have a large enough data, it reaches that bound. So that means you can have other method, at the best it be equal. It cannot be better, right? Because it already reached that lower bound, right? So there is a digression. I'm going to talk about these two methods, right? Just to explain to you. Because I'm going to give you argument in the next step about this this maximum likelihood. Maximum likelihood, actually, the population vector is a special case of the maximum likelihood method. All right? In some cases, that's very good. In some cases, not that good. To show this, you want to, when you emphasize this relationship between the least square method estimation and the Gaussian noise, the Gaussian model. Right? This is all done by Gauss, right? Because that's first. So Gauss invented. Everybody knows this Gaussian distribution invented by Gauss, but this least square estimation is a very simple method. Actually, that's also invented by Gauss by himself, and he is also the one who actually point out the relationship between the two. Right? That's actually related to the maximum likelihood. Let's see for the least square. The simplest case is that you have a linear function y equal to x. There are some parameters, right? But there are also some noise in there, right? So you've defined the square error, so y minus this whatever function, that's equal to the noise, right? Squared. And you minimize this error. Then you find out parameter like a and b. So this is also general. It could be whatever in the parenthesis may not be a linear function, could be non-linear function. All right. You could do the same thing, right? As a least square method. The Gaussian noise will have a shape like this. So if you have independent Gaussian noise, right? the probability multiply, and because it's all in the exponential, so what you have is this sum of square, right, of the variables. So here you can see the link. The link is this. So you minimize this square error, right? It's same if this error has a Gaussian distribution independent of each other, each data point independent of each other, all right? You minimize the square error is equivalent to maximize the probability for that particular case of that noise. Is that this is the probability for that particular data with this kind of error, right? So this will make your data is most likely to occur, right? Is that right? Right? So you minimize this is same as maximize this, right? Because there's a negative sign here, right? All right. So now I want to show to you that the population vector method, right? It's like based on sort of by intuition, right? But in the beginning, it's not really based on this argument. But I should say they are really related with the best possible method, like a maximum likelihood method. All right. So suppose we have this Gaussian distribution. Right? Suppose you have bunch of neuron. All right. Your code variable x could be the reaching direction. The response of neuron I is equal to have a Gaussian distribution. The mean, of course, the mean is that the tuning curve can be different from neuron to neuron. Suppose they all have the same noise, right? That's a simple case, all right? So you have a bunch of neurons. They're independent of each other. So their probability multiply, right? Then you get this, right? Proportional to the sum of all these terms. So to maximize, given this data, all right, the maximum likelihood to actually find the x that maximize this probability to make the data most likely. That's equivalent to minimizing this square term, right? So to minimize this, if you do that chain rule, you find out this equation. This is the if this f function, right, the mean firing rate equal to have this kind of a cosine tuning, this dot product term, then you will find out that this solution is equal to the population vector. All right. So basically, if your independent population, if they're independent of each other and also have a Gaussian noise, and noise is the same for every neuron. In that special case, the result, in general, is not equivalent to, in general, is equivalent to that optimal linear estimator. All right. Because you set this derivative to 0, you get this equation. This solution of the equation is that optimal linear estimator. All right. In a special case, these things, the outer product, remember, equal to the identity matrix. That condition, that's the same as the population vector. So that's the explanation why this method looks so simple. Why it sort of works, because if the noise is about the same, neurons roughly independent of each other, then this is close to the optimal. Right? Okay. So this is the optional material. I will talk a little bit more about the mathematics behind it. Right? I just very quickly just give you ideas of what this theory actually behind it looks like. Don't worry if you don't understand that. That's perfect fine. So, so what's that Cramer-Rao bound? How can you know what's the best method you can achieve? So this is very good. People, when you do data analysis, do whatever, you don't know your method is the best or not, right? If you show you can reach this bound, that's very good, because nobody can be better than you, right? That's good to know. So to calculate this bound, I just very briefly that it's based on this that probability distribution of your response. All right. You take the log function. That's also called the likelihood function, right? So how likely that is, it's a probability. You take a log and make a derivative relative to the parameter. So if I change my parameter a little bit and I change my reaching direction a little bit, how would that affect the probability? Right? You can define this as called a score function. That's the contraction of the stuff. All right. So what? Based on that, you can. So this function turns out that the s is you can regard it as a as a random variable because the response varies from try to R. It's a random variable. So this is scalar. Its average always equal to 0. Its variance is called the Fisher information. So for the information series, there are two kinds of information used most widely. Right? I think the most widely used one is Shannon's mutual information. Right? Another one is the Fisher information. Fisher information actually is actually it was proposed earlier than the Shannon information. So this Fisher information is very good for parameter estimation for continuous variables. All right. So the Kramer-Rao bound shows that if you have any estimator, right, giving you the set of data, you try to estimate the parameter. So this is the variance of your parameter, right? So every time compare with the with the average. Suppose average is equal to the true variable. This is called unbiased estimator. If your estimator is wrong, you can have variance very small. But I will always say it's 1,000, 1,000 no matter what, right? Your variance is 0, but it's wrong. It doesn't mean anything. So you have to your variable, your estimated variable should on average equal to the true variable, right? That's called unbiased estimation. So it's not possible every time you get it correct, because even though you have the same true variable, every trial the response is different. There's no way you can always get it right. There's always some error. But say that compare with your mean, the true mean, the variance has to be bigger than the inverse of Fisher information. That is a Kramer-Rao bound. So if you can achieve this minimal value, that's the best method possible. Right? So I'm not going to prove this, right? So this proof is very easy. It's based on Cauchy-Schwarz equality. It's always true, right? Just plug in the stuff and you'll see it's correct. All right. Yeah, that shows why it is correct. I don't need to explain this. So let's go back to this example. We just try to show you what's that Fisher information, right? Suppose you have this tuning function look like this, right? It is response as a function of your encoded variable has a means f of x, right? They have a variance, like a Gaussian distribution that we showed before, right? You have a tuning curve like this. You can calculate this Fisher information. It turns out like this equal to this. It's a derivative of your tuning curve, right? Square divided by the variance. So the Fisher information over here, you can see it is the inverse relationship between this. This is the minimal variance you can achieve, right? It is 1 over the Fisher information. If the Fisher information is large, this bound is small. That means the minimal error you can really reduce it, right? So that means the information large, you have a smaller error. That makes sense. So in this case, the Fisher information for this tuning curve with this noise, right, constant noise, is equal to the derivative square. That means, given this tuning curve, right, it sort of makes sense, right? So this is your variable, that's your response, right? I give you the response. You want to go backwards, see what's the variable, right? So that depends on what? Depends on the slope. It doesn't depend on the height of the tuning curve. People use intuitively always say, okay, if a cell has a lot of firing, that means give me lots of information, right? If it doesn't fire as much, it doesn't give me information. So basically, if you want to estimate continuous variable, that's actually wrong. So what gives you information? The slope. If a variable changes, how much that activity changes, right? So if the slope is larger, so this has more Fisher information. I mean, you can estimate more accurately. So that makes sense, right? If you can imagine, if if the slope is very high, right? I just move this variable a little bit. There's a big change in the response. So you go inversely. Based on response, I want to figure out what's the variable. You can be more accurate. So this part may be a surprise. So where is the point in the tuning curve that gives you the least information, the least Fisher information? It's actually at the peak. At the peak, the slope is 0. Right? It's like a flat, right? If it's a flat, that means I change the variable, the response doesn't change at all. Right? So given the response is all noise, right, I can no way you figure out where exactly is your variable. So that's kind of a counterintuitive. For a Poisson noise model, that's very similar. It's the square of the derivative divided by the variance. The variance is actually equal to the mean. It's very similar to this. It says the variance is constant here. All right. Let's just give you an example. This is optional material. It doesn't matter, but it's good to know, right? All right, so Bayesian method. So for the Bayesian method is that instead of do the maximum likelihood method like this, you maximize this, given the stimulus, and given maximize response. Is a question there? Yeah.
Define efficient information as a variance of one log likelihood or of all of them?
Which one you mean?
So here you define it as only one.
Yeah.
In that case, for a camera, I'll go.
For many neurons, you mean as increase the number of neurons? Is that right? What's the question about?
You're doing it for one sample. You're using efficient information for one sample or for all of them?
Oh, it's for average. For average all the samples. So this is for average over all samples. So it's average.
Okay. In that case, I think you need an n for a camera log value. You need 1 over n times efficient information.
Oh, you mean for this is for one. Yeah, this is for one. This is for.
Step before.
This is for one. Yes, for one. For one sample. Yeah. As you increase the number of sampling, the information increases. Yeah, it just adds up. Yeah. So, all right. For this Bayesian method, I only just add a little thing that instead of doing this, you take into account of the probability for that particular stimulus. The stimulus may be different, right? Some are more likely than others. For reaching direction, maybe everybody equal. In that case, it's the same as maximum likelihood, right? So the other case is really you want to. You may ask the question, why does that make my data most likely? Why don't I make my stimulus most likely? So that's also true. You can use this called the Bayesian formula. It's very easy, right? Based on the just Jones distribution of the response and stimulus. You can decompose in two different ways, right? Then you get this formula. This is given the response, what's the most likely stimulus, all right? So this term is the probability response. Doesn't matter. So what you try to find the most likely stimulus is the product of the two terms. Product right here. So the first term is the same as maximum likelihood. So the difference is that you should weight it by which stimulus is more likely. All right. Then you maximize this whole thing. That would be the Bayesian method. So very similar, right? Related. So okay, I'll give you the next few minutes. Give you an example. So this for these place cells, right? You saw it before. You can do this Bayesian reconstruction. So those are maximum likelihood. So this cross here is the actual position of the animal. All right. So this color map is the probability of the animal based on the instantaneous data. All right. You can sometimes you can try to based on activity you can figure out what's the location of the animal. Right. So what you got is distribution of the most likely stimulus. Here is the location. Right. You can get that distribution. Sometimes it's pretty. Sometimes pretty accurate. Sometimes there are a lot of errors. Right. But on average, you can just get a couple of centimeters. And on average, the error is pretty small. So this is more interesting that this is during sleep. This is during awake state, right? You see the movement of the animal, right, reconstructed. But during sleep, so if the animal dreaming about running in some maze in some direction, during sleep, that if the neural activity repeats, right, then you should be able to recover the trajectory, right, during the animals, whenever you see that activity. But in reality, you see the jump. The jump is really not continuous movement. It is like a visual illusion. The thing's moving, but it's very random. So based on this, you can example. This is the last example. Is that so? This is a rat. All right. Based on activity simultaneously recorded from hippocampus, you say what's the probability for animal distribution? Look like that. All right. So this trajectory event, it's 20 times faster. The animal is not moving. You see, in the brain activity when the animal is standing still, the activity actually tries to explore other places. Right. So this is for a comparison. If you really move, you can recover animal location. But when animal is standing still at that moment, looking around, the activity, see, it moving to some places. Sometimes it can actually, it can predict where animal is going to go in this kind of environment. All right, I think that's all for today. All right, thank you.